Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 23, and we're going to discuss the negative binomial distribution. If you recall from last time, we discussed the hypermetric distribution, and in this distribution, we have two types of objects. So there's N1 of type 1, N2 of type 2, and we say that N, the total population size, is equal to N1 plus N2. Little n is the sample size. X is the number of objects from the N1 type of objects available. And so the probability that our random variable x is equal to little x is N1 choose x times N2 choose n minus x over n choose little n. It can be written as N1 choose x and n minus N1 choose n minus x and n choose n. A lot of times books will do this because then you have less parameters. You have n1, n, and x. You have less variables or less things to specify, right? So it is a little more efficient that way, but I was originally taught this way, and so whichever you prefer is fine. Anyway, and there's some restrictions on x, n, little n, and n minus x as well. So this time we're going to talk about the negative binomial distribution. It's actually a generalization of the geometric distribution. The geometric distribution, if you remember, we repeated the trials until we obtained the first success. So that is a special case of the binomial distribution, a negative binomial distribution. The negative binomial distribution, we continue those independent Bernoulli trials until we get the rth, that's rth, success. And that can be 1, 2, 3. So when it's 1, of course, we're back at the geometric distribution. When it's greater, then of course it's purely the negative binomial distribution. We're going to talk about the MGF, the moment generating function, the mean, variance, and do some examples. So we're going to let x be the number of independent Bernoulli trials that we need in order to observe the rth success, and r can be 1, 2, etc. We're using the multiplication rule to get the PMF, and if we have r successes on the x try, so we have r success, the rth success on x trial, or trial x, trial number x. So that means that in the first x minus 1 trials, we had r minus 1 successes. And that's what we see here. And so there are x minus 1 choose r minus 1 different ways that can occur, because we don't care about order, we just care about the combinations. And so for those x minus 1 trials, we have r minus 1 successes, and the probability of success is p. And then we'd have x minus r failures, so q to the x minus r. So that handles the first x minus 1 trial. And then on the x trial, we have a success, and that brings us to r total successes. And so here is our PMF, and you'll notice that we've combined the exponents of p, and don't forget that you haven't defined your PMF unless you tell us what values x can take, because otherwise we can't really use this formula without knowing that information. Okay, so in fact, if it weren't obvious that p plus q have to equal 1 and that p is a probability it's between 0 and 1, then we would specify that. All right. Why do we call this the negative binomial distribution? That might be a question you're having. That was the first question I had when I first saw the distribution. I didn't see any negative exponents. And so here is a binomial of 1 minus w to the negative exponent r. We're going to use Maclaurin series and expand this. And so Maclaurin series is given here. Now this only converges when w is between -1 and +1. And remember that these h with the k in parentheses are talking about the derivatives. So we're going to start with the 0th derivative all the way up to the infinite derivative. Okay? So the 0th derivative, means we haven't taken a derivative yet. So there's 0 derivatives taken. That means we're back to the original function with nothing done to it. And so we're going to evaluate these derivatives at, in this case, w equals 0, at the variable equal to 0. So we take the derivative, then we plug in 0. Don't do it the other way, or you might end up with 0 as your answer, and that won't be right. So when we do this, we end up with 1 for the first one, for the 0 derivative. For the first derivative, we end up with r. For the second derivative at 0, we end up with r plus 1 times r. I'm starting to see a pattern. The third derivative, I see r plus 2, r plus 1, r, and now I definitely have a pattern. Now, I haven't proved anything. I've simply noticed the pattern. Proofs require induction, proof by induction. We're not going to do that, but we certainly could. All right. And so now we just looked at the derivatives, so let's plug those into our Maclaurin series for this expression here. And so we end up with 1 over 0 factorial. 0 factorial is 1, and w raised to the k, and that's 0. And then we keep plugging in, and I will let you look at these on your own and see and make sure that you understand what's going on, that we've plugged it in right. And then we simplify, and now we want to take a look at this expression here, and we've seen the pattern. So now we have to, there's nothing beside the 1 right here, so now we have to come up with a pattern for this so that we can express it as a function of, in this case, r and k. And so what I did was I took the k equals 3 situation here, and I looked at it this way, but let me look at it in reverse. This is showing you that this actually is what we have, but we really did this in reverse to come up with this formula. So we're looking at this quantity here, and I noticed that that looks like the end, the highest numbers in r plus 2 factorial. So r plus 2 factorial would give me r plus 2, r plus 1, r, and then r minus 1 factorial. So to get this here, I had to divide by r minus 1 factorial. So I have r plus 2 factorial divided by r minus 1 factorial to cancel out those other terms. And then I look at the denominator, and I see at that point 3 factorial. And so what I can do is I can say, okay, let's subtract r plus 2 minus, let's take that minus r minus 1, and that's equal to r plus 2 minus r plus 1, which is 3. And that's what we end up with here. So we have this combination. This is a combination that meets that pattern. So how do we write this in terms of k? Because here is k, by the way. So k is here. And this is 1 minus k, isn't it? Or k minus 1, I'm sorry. So k minus 1. So this is really r plus k minus 1 on the top. And then we have r minus 1 and then k factorial. And so that is r plus k minus 1, choose r minus 1 as a combination. That's how we got that. Okay. So now we're going to do a substitution, x equals k plus r. We solve for k, we get x minus r. We are going to substitute that in and look at our original binomial here. And when we do that, we end up with this expression here. And remember that w is still between -1 and 1. Now we're going to make another substitution, w equals q, to put it back into terms of our negative binomial. And we see that this expression for 1 minus q to the negative r gives us this summation of the first part, or of part of our PMF. Our PMF, if you remember, if we go back here, our PMF has this, and this, and we're missing the p to the r. Well, p to the r doesn't have anything to do with k, and so we can just, to get our PMF, we can multiply by p to the r, and of course we can bring it inside the summation here, and now we have the sum of our PMF from x equals r to infinity. Remember, r starts at x starts at r, and we know that this portion here is 1 minus q to the negative r, and so we plug that in, and 1 minus q is p, and so we have p to the negative r, p to the r, that gives us 1. We have a PMF. Remember that all the terms have to be between 0 and 1 of a PMF, and they're all positive, and none of them are greater than 1, and they couldn't be greater than 1 because the total's 1, and we'd have to have, if one term was greater than 1, we'd have to have some negatives in there, and of course you can't have negatives for a PMF, and we don't. So we do have a PMF here. So if we let r equal 1, then x becomes a geometric distribution with parameter p. And we go back to the geometric distribution PMF. So if you substitute that in for the negative binomial, for r equals 1, you will see that it reduces to this. And here's a general form of our geometric series. We've added the constant a here. And so if we're going from k equals 0, then to infinity, we get this answer. I also wanted to put in here a nice technique here. If I don't want to start at k equals 0, I can start at k equals 1, so I've increased k by 1. I have to increase this number by 1 as well, but infinity plus 1 is already infinity. And so notice what happens to our exponent. We have to decrease it by 1. So this exponent goes in the opposite direction of where we start here. So if where we start goes up, then this goes down. All right. And remember that r, absolute value of r, is less than 1. Now, for the geometric distribution, we can look and verify that we do have a PMF. Now, we just did that for the negative binomial, which includes this special case, but we're doing it especially for this one by itself. Now, k is a positive integer, and when we have k equal to a positive integer, this is still for the geometric distribution, then we can start at k plus 1 up to infinity, and when we start at k plus 1 up to infinity for this expression, then we get this expression, which simplifies to q raised to the k. That's really nice to have. We now know that the probability that x is greater than some value k is equal to q raised to the k. So an easy expression for that. And when we have the greater than, we can figure out the less than or equal to as well, which is our CDF. And so our CDF ends up being 1 minus q to the k equals 1, 2, etc. for the geometric. Again, this is the geometric, not the general negative binomial, but the specific case of the geometric. Now let's look at the moment generating function for our negative binomial. Here we have m of t equals e raised to, or e expected value of e raised to the t times x. And so remember that the expected value is whatever we're taking the expectation of times f of x, and we take the sum of that. And since our negative binomial starts at r, we start our sum at r as well. So you can see where this is really important to specify what x is, because otherwise these sums might be off and you might come up with a really bad result because you're not, you don't have all the details. Okay, so we've done a trick here where we've taken e raised to the tx, and we've noticed that we have q raised to the x minus r. Okay, and so we want to combine e with the x minus r, but to get x minus r, we have more than that. We have x. So what we do is we break out, we say x minus r, and then the difference is e to the t raised to the r. So we have to multiply that so that we don't change it, so that we're still end up with the same expression. But now we can combine these. So that is the technique, the major part of this proof that you need to understand. And so when we do that, we end up with this expression with our restriction on t less than negative ln of q. Now, to get the mean and the variance, we need to take the derivative of the moment generating function, which I've done here, and here is the final form of that. So I'll let you look through those calculations, make sure you can follow it. Here I've used the quotient rule for the first derivative, and then you'll notice I expressed it as a product. So for the second derivative, instead of using the quotient rule, I used the multiplication rule. And then I plugged in 0 for the first derivative and ended up with this very nice, easy expression for the mean. And this is the mean of the negative binomial, not the mean, which we've already gone over for the geometric. Of course, it works. If you put in 1 for r, that's 1 over p. That is the mean for the geometric distribution. And then we plug in 0 for the second derivative. And we end up with this nice expression for the variance. So when I plug in 0 for the second derivative, I end up with the second moment, which is e of x squared. And so that's this expression here. But remember that the variance is ex squared minus ex quantity squared. So it reduces to this nice equation for the variance. All right, so that's our lesson for today. Don't forget to scan in your lecture notes and upload them to the Google Drive folder by midnight of the date listed on the course calendar. You might want to update your formula sheet. You certainly want to update your list of distributions with the negative binomial, the mean, the variance. You'll want to update your geometric distribution with the moment generating function. If we haven't gone over that before, you can do the special case here, and with your CDF and P of x greater than k for the geometric distribution. If you have questions, come to virtual office hours. If you can't make those and you need an answer, email me. But email me a picture of your work and a picture of the problem, because I might not have access to that, and then I wouldn't be able to help you until I have access. So this will make it faster for you and for me. So take care, and we will see you next time.